What is the universe made of? How did it come into existence? Was there anything before it? Where did the laws of nature come from? As difficult as these questions are, scientists are grappling and attempting to address them with bold new ideas and new experiments. By combining mathematical models with observations, they are able to develop workable theories of how the universe came to be. Over and over again, the universe has proven to be far stranger and more complex than we even begin to imagine. Astronomers have put forth numerous hypotheses and explanations of the origin of the universe. The Big Bang Theory is the prevailing cosmological model explaining the existence of the observable universe. It postulates that the universe began in a tremendous explosion about 13.8 billion years ago. During those earliest moments, the universe was filled with energy, much of it in the form of intense heat. As the universe grew and cooled, some of this energy transformed into matter. We once thought that the atoms were the most fundamental building blocks of matter. Today, we know that atoms are made of many smaller pieces, known as subatomic particles. Professor Brian Cox is a British physicist and professor of particle physics at the University of Manchester. He investigates the universe's biggest questions and explains what these particles are and their role in the creation of the universe.
So we know today that the universe is built of just these things. These are the fundamental building blocks of the universe. These two things may be slightly familiar. They're called up and down quarks. The proton is made of two up quarks and a down quark, and the neutron is made of two downs and an up. So those two things are the building blocks of the atomic nucleus. And that's what you need to build you and me and the Earth and the stars and planets and everything we can see in the sky, we think is made of just those, the up and the down quarks and the electron. This thing, called the neutrino, completes the set of these four, and in fact, in the process the sun goes through converting hydrogen into helium, it produces copious quantities of these things called neutrinos. So many, actually, that if you hold your thumbnail up now, there are something like 60 billion neutrinos per second going through your thumbnail from the sun. You don't feel them because they interact very weakly with normal matter, but they're there and they allow the stars to shine. So they're important, and that's all you need to make a universe as far as we can tell, just those four particles. For some reason that we don't understand at all, nature saw fit to make two carbon copies of those, as it were. These are identical in every way to those four particles, except they're heavier. So this thing is called a muon. It's the same as an electron in every way, except it's heavier. This is a tau, same as the electron and the muon in every way, except they're heavier. So that's one of the great mysteries in physics, actually. Why has nature chosen that pattern? You only seem to need 4 to build everything. Nature has got 12. As you go back in time, what happens? Remarkably, when you go back to the first second, or the first thousandth of a second, or the first millionth of a second after the Big Bang, you find that the universe was extremely simple indeed. So our picture is that the universe has been expanding and cooling ever since it began, and getting more complicated. So things like you and me, and stars and planets and galaxies, these complicated structures that we see out there in the universe, are in a sense properties of an old and cold universe. Right? In a sense, they've crystallized out. But if you sweep back in time, the universe, well, that structure melts away as the universe gets hotter, and you find a very simple universe indeed, a universe that we can understand to a large extent.
Observations by NASA's Cosmic Background Explorer and Wilkinson Anisotropy Microwave Probe revealed microwave light from this very early epoch, about 400,000 years after the Big Bang, providing strong evidence that our universe did blast into existence. Since the beginning of the 21st century, the way the universe is viewed has changed dramatically. As of September 2021, more than 4,800 planets have been discovered orbiting distant stars. Black holes are now known to be present at the center of most galaxies, including the Milky Way galaxy. The age, size, and shape of the universe have been mapped based on the primordial radiation left by the Big Bang, and it has been learned that most of the matter in the universe is dark and invisible, and the universe is not only expanding, but accelerating in an unexpected way.
This is one of the great mysteries. It turns out that everything's accelerating in its expansion. So literally, as you look at the more distant galaxies, they're not, you might expect that because gravity is an attractive force, everything got blown apart at the Big Bang, and then it was all trying to attract itself to everything else, and so it'd be slowing down, right? And that's what everybody thought. Everybody just thought, well, the universe must be, it started off in a Big Bang, and it must be slowing down. But actually, it turns out it's accelerating. Now, that implies that it will be around forever, and it will continue to expand forever. But the mechanism that causes the acceleration is not understood at all. We call it dark energy, so it's got a name. It turns out something like 70% of the energy in the universe is taken up in this accelerating expansion, but we don't know what it is. The other great question, which is a bit more, perhaps a bit easier to see that we might get an answer to, is that another 26% of the universe is made up of something called dark matter. There's a lot of stuff we can't see, and we don't know what it is, and it's something like 96% of the universe. So that's kind of a bit embarrassing.
The universe is comprised of mostly hydrogen and helium. In fact, these two elements make up 98% of the visible matter in the universe. Nevertheless, our planet and everything it contains, even life itself, is possible only because of the existence of heavier elements such as carbon, nitrogen, oxygen, silicon, iron, and many, many others. In order to understand how the universe has changed from its initial simple state following the Big Bang into the magnificent universe we see as we look at the night sky, we must understand how stars, galaxies, and planets are formed. Present observations suggest that the first stars formed clouds of gas around 150 to 200 million years after the Big Bang. Heavier atoms such as carbon, oxygen, and iron have since been continuously produced in the hearts of stars and catapulted throughout the universe in spectacular stellar explosions called supernovae. New results from the NASA ESA Hubble Space Telescope suggest the formation of the first stars and galaxies in the early universe took place sooner than previously thought. The earliest formation of stars and galaxies occurred much earlier than can be probed with the Hubble Space Telescope. This leaves an exciting area of further research for James Webb Space Telescope and more powerful instruments that will be designed in the future. There is a limit, however. Our understanding of the laws of nature permit us to track the physical state of the universe back to a certain point where the density and temperature were really high. Beyond that point, we don't know exactly how matter and radiation behave. This does not mean the universe began at that time. We simply don't know what happened before that point.
So the problem is to do the following. We want to guess about how this structure emerged, and then we want to do experiments. But we want to do experiments back here. What we really want to do is build a time machine and sweep back to the first billionth of a second after the Big Bang or before and observe what's happening in the universe. We can't do that, unfortunately. But what we can do is recreate those conditions in a lab, the conditions of very hot, very dense, very energetic space. And this is the lab that we do that at. It's called the Large Hadron Collider at CERN in Geneva. 27 kilometers in circumference. It's the biggest scientific experiment ever attempted, the biggest scientific experiment ever built. Its job is to take the nuclei of hydrogen, so the simplest element, single protons that make up the atomic nucleus of hydrogen, and accelerate them to 99.999999% the speed of light. And we do that with two beams of protons. One we send around one way, one we send around the other way, and we collide them together. In every one of those collisions, we reproduce the conditions that were present less than a billionth of a second after the universe began.
Some scientists, such as Roger Penrose, a 2020 Nobel Prize winner in physics, believe there have been multiple Big Bangs and that more will happen in the future. Yet, many others think that the universe may have expanded from an initial point known as a singularity. As James Hartle and Stephen Hawking proposed, the cosmos may have had no temporal beginning at all, but rather a rounded-off cap of pure space. According to them, asking what came before the Big Bang is meaningless because there is no notion of time available to refer to. To put it simple, it would be like asking what lies south of the South Pole. Stephen Hawking's approach to the universe considers space-time to be a hologram in which the geometry of the entire past would project off the present. Brian Cox also agrees that we might be holograms and suggests that it's possible the universe might not be at all as we perceive it to be. But more on that in another video. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.